What if I told you we already have almost everything we need to build a fully reusable spaceship that can fly to the moon and back? Not in 50 years, not with science fiction technology, today. The biggest obstacle isn't faster engines, it isn't nuclear propulsion, and it's definitely not a lack of brilliant engineers. According to modern aerospace engineering, nearly 90% of technology already exists. So why hasn't anyone built it? The answer comes down to one brutal equation that's defeated engineers for decades. In this video, we're going to design a real moon-capable spaceplane using existing technology, uncover the engineering problems that make it so difficult, and discover why the future of space travel may depend less on inventing new technology and more on combining what we already have in ways no one has before. By the end, you'll understand why the future of spaceflight isn't science fiction, it's systems engineering. Before we design a spaceship, we have to decide what it's actually supposed to do. Our spaceship has to launch from Earth, reach orbit, refuel in space, fly to the moon, support a crew, return safely through Earth's atmosphere, and then land under its own power, ready to fly again. It's extremely demanding. Airplanes only fly through the air, submarines only operate underwater. This vehicle has to survive Earth's atmosphere, the vacuum of space, lunar operations, and an extremely hot re-entry. Every system has to be carefully designed to work with each other. And every great machine starts with a frame. Cars have chassis, buildings have steel beams. Our spaceship needs a skeleton capable of surviving millions of pounds of force. The primary structure would be built from carbon fiber reinforced polymer. The carbon fiber gives us incredible strength while keeping weight as low as possible, because every extra kilogram means even more fuel. But carbon fiber isn't perfect. Where will the engine mount? Where will the landing gear attach? Where will the wings transfer aerodynamic loads? We reinforce everything with titanium alloy load paths. Titanium acts as a spacecraft's bones, spreading enormous force throughout the structure. Unlike a traditional rocket, the body itself helps generate lift during re-entry, reducing stress on the vehicle and giving the flight computers much greater control during landing. At this point, we've only built an empty shell, but that shell is already doing multiple jobs. It's carrying launch loads, protecting the crew, supporting the fuel tanks, and providing attachment points for every subsystem we install next. Everything from this point forward depends on the structure, and now we need something to put inside it. Most people think engines are the heart of a rocket. They're not. Fuel is. Hidden inside the spacecraft are two enormous cryogenic tanks. One stores liquid methane, the other stores liquid oxygen. They're kept completely separate until they reach the engines. Both liquids are chilled to incredibly low temperatures, which means the tank needs heavy insulation to keep the propellant from slowly boiling away. But here's the clever part, they aren't just storage tanks, they're incredible structural members. The tanks help support the vehicle itself, transferring loads to the spacecraft during launch. Every kilogram saved here increases the payload we can carry to orbit. So our spacecraft has a skeleton. Our muscles are full of stored chemical energy, but we need a way to release it. That's right. Let's talk about the propulsion system. Our primary engines would burn methane and liquid oxygen using staged combustion engines similar to today's most advanced reusable rocket engines. When the flight computer commands ignition, powerful turbopumps force both propellants into the combustion chamber at enormous pressure. Inside the chamber, the fuel ignites. Expanding gases race through the engine's nozzle at incredible speed, creating thrust. That thrust does not push against space. It pushes against the engine frame. The engine frame pushes against the titanium structure, and the titanium structure pushes on the rest of the spacecraft. That's how the entire vehicle accelerates. These engines perform almost every major maneuver, launching from Earth, reaching orbit, leaving Earth orbit, landing on the moon, returning home, and landing back on Earth. But rocket engines aren't the only propulsion system on board. Once we're in space, efficiency is king and becomes far more important than raw power. Ion thrusters take over long-duration orbital adjustments and trajectory corrections. They're far too weak to launch from Earth, but they're incredibly efficient using only tiny amounts of propellants over weeks or months. Chemical engines provide power, electric engines provide efficiency. Together they allow the spacecraft to operate completely different environments, but the engines don't do the work alone. They need electricity. Once safely in orbit, large solar arrays unfold from the spacecraft. They become the vehicle's primary source of electrical power. Electricity flows into a power conditioning hardware where voltage is regulated before charging lithium battery banks. From there, a central electrical distribution bus supplies power to every subsystem on board. I'm talking flight computers, navigation, life support, communications, sensors, electrical propulsion, thermal pumps. Every electronic component depends on the single electrical architecture. The battery provides backup power during eclipses, engine burns, and peak electrical demand. In the future, compact nuclear reactors may replace solar panels, but today's solar panel is lighter, simpler, and it's already proven. But we do have one more problem. People. Building a tiny Earth isn't easy. Space is trying to kill you every freaking second. There's no air, no pressure, no water, no oxygen. Inside our spacecraft, life support literally creates a mini Earth. Carbon dioxide exhaled by the crew passes through scrubbers and it's removed from the cabin's atmosphere. Oxygen is then recycled back into air. Water from condensation, hygiene, and other onboard systems is going to be filtered and then reused. Cabin temperature and humidity are constantly regulated, and emergency oxygen reserves remain available if anything goes wrong. Almost every one of these technologies already exists aboard, you guessed it, the International Space Station. Our challenge isn't inventing life support, it's making it smaller, lighter, and reliable enough to fly inside a reusable spacecraft. But keeping people alive isn't just about air, it's also about temperature. Most people think spacecraft only have one heat problem, but they actually have two. The first is thermal management. Every computer, battery, electrical system, and astronaut, guess what? They produce heat. In space, there's almost no air to carry that heat away, so coolant loops run throughout the spacecraft, collecting waste heat from every subsystem. That heat travels through the heat exchangers before eventually reaching large radiators where it's slowly emitted into space. Without this system, the spacecraft would literally cook itself from the inside. Then comes the second challenge, re-entry. Returning from the moon means smashing into Earth's atmosphere at nearly 25,000 miles per hour. Air compresses in front of the spacecraft until temperatures will rise higher than molten lava. To survive this, the spacecraft is going to wear ceramic heat tiles across most of its surface. One system keeps the spacecraft cool during the mission, the other prevents it from burning apart at the very end. Our spacecraft can only fly if it knows exactly where it is. That's the job of the avionics system. Inside the spacecraft sits 3 independent flight computers operating in what's called triple modular redundancy. Every computer constantly checks the others. If one begins producing bad data, the other remaining 2 outvote it automatically. The spacecraft keeps flying. Navigation data comes from an entire network of sensors, GPS while near Earth, star trackers while in deep space, inertial measurement units measuring every tiny acceleration, radar and LiDAR guiding autonomous landings, fault detection software constantly monitors every pump, valve, battery, engine, and computer, and artificial intelligence assists with route optimization, landing support, and predicting equipment failures before they happen. Humans always remain in control, but AI acts like an incredibly experienced flight engineer working 24 hours a day. Now we got to talk to Earth. Near Earth, standard radio systems handle communication, but once it leaves Earth, a high-gain antenna is going to be your primary connection. Telemetry, commands, crew communication, navigation updates, everything flows through this communication system. Now, when we get beyond Earth's magnetic fields lies one of the mission's greatest dangers, radiation. Solar particle events and galactic cosmic rays constantly bombard deep space. To protect the crew, the spacecraft includes a heavily shielded, safe area surrounded by water tanks, polyethylene shielding, and titanium structural elements. The computers themselves use radiation-hardened processors and error-correcting memory designed to survive environments that would constantly destroy ordinary electronics. This is another example of systems working together to create a better solution. Water is not just drinking water, it's going to be radiation shielding. Structure is not just a structure, it's going to protect you from cosmic rays. Every component serves multiple purposes whenever possible. By now, we've built an incredible spacecraft, but there is one more problem. It cannot reach the moon efficiently. Without orbital refueling, the spacecraft has to launch carrying every kilogram of fuel needed for the entire mission. Launch, moon transfer, landing, return, Earth landing. That's going to make the vehicle absurdly heavy. You're having towers of fuel being used to carry more towers of fuel. Instead, multiple tankers launch, fill an orbital depot. Our spacecraft reaches orbit with nearly empty tanks. It docks to the depot, refuels, then leaves Earth carrying only the fuel actually needed for deep space. This is one piece of infrastructure that changes everything. It reduces launch mass, increases payload, and makes it fully reusable practical, and turns an impossible mission into an achievable one. Alright, we've made it. Let's put it all together now. Imagine launch day. The engines ignite. Thrust flows through the titanium frame into a carbon fiber structure. The cryogenic tanks feed methane and oxygen into the engines. Flight computers are continuously adjusting engine thrust and steering. Sensors are monitoring thousands of data points every second. Electrical system powers every onboard subsystem, and life support is keeping the crew alive. But thermal management is going to remove that heat waste and communications stream telemetry back to Earth. After we reach orbit, the solar arrays deploy, the batteries recharge, orbital refueling tops off the tanks, and electrical thrusters are going to make tiny trajectory corrections during the journey to the moon. On the way, radiation shielding is going to protect the crew from deep space travel, and on the return trip, thermal control systems prepare the spacecraft for re-entry. The heat shield absorbs temperatures hotter than lava, flight computers guide the descent, the engines ignite one final time, and the landing gear deploys. The spacecraft touches down under its own power. Every one of those events depends on dozens of independent systems operating together flawlessly. Remove any one of them, the mission fails. Here's the part that might surprise you. We did not invent a warp drive. We never discovered anti-gravity. We never needed some impossible new material. Everything we used already exists. Carbon composites, reusable methane engines, ion thrusters, solar arrays, the life support on the ISS, autonomous landing systems, radiation-hardened computers, and ceramic heat shields. The challenge has never been inventing the future, it's integrating the future. Hundreds of existing technologies into one vehicle that needs to perform the most difficult missions humans have ever attempted. The future moonship probably won't be remembered because it introduced one revolutionary invention. It will be remembered because it proved that when every subsystem works together as one machine, the impossible suddenly becomes possible.